All right, today we're going to do some intersecting of polar graphs. We're going to look at two different methods. One is using our calculator, and one is doing it algebraically without a calculator. There are some graphs where it's not feasible to do it by hand, but when we can, we would like to. And for Calc 2, when you go on, you're going to need to be able to do both. So let's start with a little calculator intersecting first. So you will want your calculator out. Right here I have the graph of 3 plus cosine theta and 5 sine of 2 theta. Hopefully you recognize the four-leafed rows as the 5 sine of 2 theta and the circle as 3 plus cosine theta. And if we think about how many intersection points there are and we just look at the graph, it appears that there are 1, 2, 3, 4, 5, 6, 7, 8. However, we will discover that there are not actually 8 intersection points, and it has to do with the fact that in polar, every point can have multiple names, and we need to be at the same r coordinate, at the same place for the same angle, and that is not always true. Now, if we look at these graphs themselves, so if you put these in your R1 and R2, I have a window that goes from negative 6.5, negative 5 to 5 for y. And I'm going to do one more thing. I am going to go to, is it mode? Yes. I'm going to go to mode, and I am going to graph my two equations simultaneously, which means they're going to graph out at the same time, and you can see the difference between what we call a collision point, a true intersection, and where it just the graphs appear to be on top of each other. So here we go. And I also, in my r equals, let's do this. If I select the ball, it makes it much easier to see the path as they're going. So here we go. And there they're going. So that's an actual intersection. There's another one. So in the first quadrant we had 2. There's a third and the fourth, because they're in the same place at the same time. Right? So if we come back to our graph over here, it looked like only this, this, and this are our true intersections. Okay? As I trace, and one other change I'm going to make, if you go to Format, you can look at rectangular versus polar graph coordinates. I'll show you what the difference is. If we go to Trace, and I trace, notice I have theta right up here, but it's x and y coordinates, which is not particularly helpful. Those are my rectangular coordinates. So if you go to Format and then go over to polar graph coordinates, now when I trace, you can see I have r and theta. And as we trace around, like, go back a little bit, right there at about 25 degrees, r is 3.9. And if I switch to my other equation, it's about 3.8. So those are in about the same spot. But if I keep going and I look at what happens when I'm over here, right, at about 110 degrees, when I switch graphs, I switch way to the other side. I'm on the rows, I'm in quadrant 4 instead of in quadrant 2, because if you notice right here again, r at 110 degrees on the rows 5 sine 2 theta, r is negative, so it graphs in the opposite direction to 110 degrees. And that's why our red dots on the graph on the right are our only true intersections. Now, so we want to find the exact points. And I go to second trace, which is where I go in y equals mode, and I try and intersect. And unfortunately, you cannot intersect in polar. We can trace, and we can try and make our theta steps smaller so that we can get closer and closer in. But we are about precision. We are mathematicians. We want to be exact. And so while it is excellent to look at our graph in polar mode to get a sense for what it looks like to actually get your intersections, function mode is where it's at. So we're going to go back to function mode, and I'm going to put in my two equations again. So I have 3 plus cosine theta, and I have 5 sine 2 theta. And I'm going to need a different window now because x is now my theta, and I want angles from 0 to 360. We're going to see the intersections in one trip around. And now I need a bigger x scale as well. I think my y scale will be fine because 5 sine 2 theta doesn't go any higher than 5 or negative 5, but we'll check. My x scale, let's look at maybe by 30 degrees. And let's look at our graph and see how that goes. Yes, I will be plenty high enough. And now you can see as we graph this, again, this graph shows our 4, not 8, 4 true intersection points. And to find the intersections, I do my second trace, and I hit intersect. And again, it's going to ask me which curves do I want to intersect, and I hit enter, enter. And you can cursor over. I'm a big fan of guessing. I see my first one is somewhere around 30, 33. Whoop, not 330. That's not what I wanted to do, but it'll work. It'll just get me the one at the end. Oh, no sign change. Let's try again. Let's try trace. Nope, second trace. I want to intersect. So let's do first curve, second curve. I want it to be about 30 degrees. And so there's my first intersection. Remember, x in this case is theta. So at 25.644 degrees, and y is my r will be 3.901. That's going to be on both graphs, right? And then I can continue on in this manner and find a different intersection. Again, the next one, I'm going to hit enter, enter, but I'm going to guess more like 60 because it seems like it's about 60 degrees on my x scale. And there it is at 68, right? And so I can get my 4 intersections that way. So when you want to use your calculator to find your intersection points, it's helpful to look at them in polar mode, having your graph set to oops, not that part, mode. There we go. If you're in simultaneous, you can see how they graph and see which are actual intersections and which are not actual intersections, so our true collision points. And then the other thing is then to actually find them, it is much easier to do it in y equals mode.